Good morning. My name is Mehaa and I am a junior in the Global Studies Academy at Travis High School in Richmond, Texas. Water scarcity is a fast-growing issue across the globe. As you can see the dark colored sections of this map, nearly half of the world faces water-related issues every day. Unless we make minor adjustments in the way we utilize water, we may have to make huge compromises in the future. Here is an animation on how gray water is collected, stored, and reused. In this project, gray water is collected only from the shower to investigate issues related to shower water recycling. A typical toilet tank is designed only for using a single source of water, fresh water. The reason for my suggestion to not use the freshwater inlet for gray water is due to the complications of cross-contamination, particularly when there's a need to switch between gray water and fresh water. Accordingly, if the toilet flushing system is designed with the dual water inlet, then the valuable fresh water can be easily isolated in the toilet whenever the gray water is available. In order to convert an existing toilet flushing system to a dual water toilet flushing system, I needed a second hole in the toilet tank. I drilled another hole in the bottom of a ceramic toilet tank for the gray water. If another fill valve is installed in this new hole, immediately an obvious 50% freshwater savings is obtained, because half of the tank capacity can be filled with gray water. 50% savings is very low, and the objective of this research was to achieve greater freshwater savings, which requires a novel design to keep the freshwater valve closed during the gray water flow. This is ARIA installed in a toilet with the gray water collection system. This is the hole I drilled. This is a small gray water receiving tank inside the toilet flushing tank, which encloses the freshwater valve and its float. With this new design of a gray water receiving tank surrounding the freshwater float, the freshwater float moves up and down with the water level in this small tank, compared to moving up and down with the water level in the main tank. Note that the gray water receiving tank must have a drain hole so that when there is not a gray water supply after flushing, the small tank will be emptied to let the fresh water flow in. The drain hole has some specific requirements, as the following. It cannot be too big to ensure that the water does not drain too quickly from the gray water receiving tank during flushing as long as the gray water is available. It cannot also be too small because that will create a long delay in filling the tank when the gray water is unavailable. The drain hole design was a major task in this research, so I decided to attach a check valve, but I modified the functionality of the check valve. The valve will now have a function not as a check valve, but as a level-based control valve, which will close and open based on the water level in the main tank. This design includes attaching a rod to the door of the check valve and attaching a float at the end of the rod. When there is no water in the tank, the valve will open completely due to the weight of the float, free from any buoyant force. When there is a minimum amount of water in the main tank, the valve will be kept closed, similar to the traditional ball float principle. One of the accidental discoveries during my research ensured 100% freshwater savings. During each flush, when this lever is pushed, this rod connected to this float is mechanically lifted regardless of the water level in the main tank. When the rod is lifted, the drain hole is closed, and the freshwater valve remains closed. This achieves 100% freshwater savings. Here are the following steps required in assembling ARIA. Here is a simulation of how ARIA works. As soon as the gray water fills a small tank, the fresh water stops, and the gray water overflows from the small tank into the main tank. The gray water also fills the main tank and finally stops the gray water by the action of the gray water flow on the gray water fill valve. Here is a simulation of how ARIA works when there is no gray water available. In this case, the fresh water will fill the main tank first, and then it will overflow back into the small tank, to stop the freshwater valve. The height of the drain hole from the bottom is an important parameter. It determines the transient profile of the water level in the small tank. Indirectly, it determines whether the freshwater valve will open or not. To achieve 100% freshwater savings, I determined what minimum gray water flow is required for a particular design of ARIA with its drain height. The minimum gray water flow also determines the minimum gray water pressure required. I studied the flow requirement using a model of the tank. My theoretical model of the system includes 3 equations. 1 for the material balance of the water in the small tank, 2 for the material balance of the water in the main tank, and lastly, Bernoulli's equation relating the water level in the small tank and the draining flow rate. I was mainly interested in the change of the water level as a function of time inside the small tank. This plot shows the height of the water level inside the gray water receiving tank versus the time for various gray water flow rates. After adjusting the float height to a required height of 1.5 inches for the freshwater valve to open, the flow required to avoid opening the freshwater valve is the minimum gray water flow rate. I calculated this flow rate theoretically based on the design parameters and verified it with experimental data for every one of my prototypes. This helped me to fine-tune the design of ARIA. The minimum gray water flow required for ARIA is 2.3 gallons per minute. Although I had 2 other successful prototypes, I call my most efficient prototype ARIA. This video shows what happens during a flush with a dual water toilet flushing system. Pay close attention to the black tube. As you can see, there is no freshwater flow because after flushing, the gray water rushes into the system, preventing the freshwater flow, resulting in 100% freshwater savings. Here is a table that shows the evolution of my design that led to ARIA, that has adjustable parameters, which is optimized to work with the minimum possible gray water flow. Gray water collection and purification is the second part of my research. I also wanted to install a system in a single-family, permanent home to bring out the practical difficulties involved. Gray water purification has been discussed by several researchers, and there are only a few purification systems being sold in the market. One of these manufacturers claimed to obtain purified water, gray water, as clean as potable water. The real question is, how much energy and maintenance is required for any sophisticated technology applied for the purification? Gray water purification requirements significantly vary based on the source itself. For example, recycling kitchen water is the most difficult task due to the very high levels of organic materials and solids. Most studies in the literature, including ones from Malaysia, consider gray water as the water from all the usage points combined, except for black water, which is the water from toilet flushing. Their objective is mostly to ensure cleaning the gray water sufficiently enough to release it into ecosystems, such as rivers and lakes. Gray water purification becomes a bigger issue when all the gray water, including the water from kitchens, is combined. If a house inhabits an infant, the gray water also exhibits higher bacterial presence. Phycoremediation with indigenous microalgae is often used for gray water treatment, and the process requires a treatment time of a couple weeks. The gray water purification in my research is purely for toilet flushing. Based on the amount of water generated in the shower and daily water requirement for toilet flushing, there is a very good balance between the two to notice any overflow of the gray water tank. However, the water can slowly accumulate in the gray water tank over a long period. My research objective is to implement a shower water recycling system and evaluate the nature of the water quality issues in a regular usage environment. Everyone knows that plumbing modifications for gray water recycling are essential. And when I first decided to survey on how to collect gray water, I thought about several ideas. There are three possibilities for the location of the gray water tank. If I had to keep the gray water tank in the attic or outside the house, piping requirements were obviously extensive. Several gray water purification products sold today include a gray water tank that can be easily kept inside the home, even inside a bathroom. Independent of the location of the gray water tank, the point of gray water collection is critical in my case because it involves breaking the sewage line, which may also involve digging if the piping is underground and the bathroom is on the ground floor. Without much invasive plumbing, I wanted to demonstrate a simple methodology to collect the shower water, purify it, and reuse it in the dual water toilet flushing system to investigate odor-related issues, because the most common issue discussed in the literature is a potential possibility of odor of the gray water. My hypothesis is that if you do not store the shower water for too long and drain it out regularly after using it for toilet flushing, there should not be any odor issues. When I decided to implement a shower water recycling system, I surveyed all three of the bathrooms in my house. When I decided to use the bathroom in the ground floor, it has a drain that cannot be accessed either without digging. But I was looking for a simpler method. More than the methodology on how I collect the shower water, studying its characteristics based on the storage time was my main interest. I was looking for a simpler method to collect shower water, and I tried a few. For example, I tried to see if it is possible to add a hollow platform on the shower basin to collect shower water, from which I could try pumping the water to the gray water tank. I even installed a platform that is normally used for collecting spilled oil from barrels. My sister and other family members started complaining about the odd feeling due to the raised level in the shower, and then I just abandoned the idea. I'm discussing this because gray water recycling involves some changes inside the house, and family members should be a part of the decision in many ways. I started thinking about ideas that would not cause any discomfort for others in my family. If I had to build a new home, I would definitely just split the sewage line with a couple valves to direct the gray water to an engineered pit, and would have used a sump pump to pump the water to a gray water tank that is kept outside the house. I was trying to find out what kind of modifications could I suggest to home builders for a gray water ready home. My objective in this research, as I already mentioned, is to collect the relatively clean shower water and to use it in the safest way, which in this case is toilet flushing. An interesting study on the probability of contamination that leads to a disease by recycling shower water for toilet flushing was done by Shi et al. This strongly concludes that the possibility of contamination by shower water recycling for toilet flushing is almost close to nothing. Several studies also support the idea of short-term shower water recycling for toilets, but my objective is to combine the short-term shower water recycling with ARIA, because when you implement short-term shower water recycling, there is a frequent possibility of not having enough gray water. And by only using a single water inlet toilet system, it might involve a lot of manual work to switch between the fresh water and gray water. That could lead to some uncomfortable situations. But first, I needed to stop the water from going into the drain. A simple rubber-based drain stopper did the work without wasting a drop of water. When the water started collecting, I realized that the outside floor of the bathroom is half an inch deeper than the shower basin. Then, the only major structural change required was to drill a hole in the shower basin and the attachment of a tube to collect the water in a small open bowl next to the shower. Then I looked at several pumps, and I realized that a sump pump is perfect for pumping this water to the tank. These pumps are designed to start and stop automatically based on sensing the presence of water, so I decided to only use microfiltration for my study. I installed a Culligan P5 cartridge-based filter that filters up to 5 microns and used CPVC pipes to connect the pump to the tank. I bought a gently used barrel that was originally used for the international shipping of pickles, which was fitted with overflow lines with multiple drain holes. I then installed the tank in my bathroom on a table and equipped the tank with a drain line and an overflow line. I used a pump that has an automatic on-off feature based on the discharge pressure. I also installed a level sensor to sense the water in the tank to disable and enable the pump. I also connected a pressure release valve in the discharge of the pump to avoid overpressure in case of any pump switch malfunction. The dual water toilet flushing tank is equipped with both fresh water and gray water through a buffer tank. Note that the pumps will be running only when someone is in the bathroom, and there is no situation when any of the pumps have to run when neither the toilet nor shower isn't used. I might even add a motion sensor with a timeout relay so that even by default, these pumps will not run in the absence of someone in the bathroom. Additionally, there is a pressure indicator connected to the buffer tank between the pump and the toilet flushing tank. These are the detailed specifications of the materials that I used in my design. The analytical instruments that I used are a dissolved oxygen meter, a pH meter, a total dissolved solids meter, and a turbidity meter. After installing and commissioning the gray water recycling system, I divided my research duration into a series of 10 days. During each 10-day period, I did 3 experiments. It included storing the gray water for 1 day, 2 days, and 5 days. I measured DO, TDS, turbidity, and pH for 5 different samples for each storage methodology. Let's get into the BOD5 analysis. Measuring TDS, turbidity, and pH are straightforward, but BOD5 is measured over a period of 5 days. The difference in the dissolved oxygen between the start and the end of the 5-day period maintained at 20 centigrade is called BOD5. BOD5 measurements for gray water did not require any dilution. Here are a few snaps of my gray water recycling system. I collected 25 samples over a period of 9 months. The green and the purple trends show the dissolved oxygen of filtered and unfiltered water for the entire duration. From April to January, the raw water DO increase could be due to the temperature difference between summer and winter. The blue, yellow, and cyan plots indicate the consumption of DO in 3 cases over a period of 5 days by the organic compounds in the gray water. Next is the plot of the BOD5 measurement for these 3 cases, and it is easy to see the BOD5 values start to increase after 5 days. pH measurements did not show any significant difference based on storage time, and total dissolved solids also did not show any variation based on storage time. Since the filtered water was very clear, the turbidity value also remained below 10. The storage time definitely affected the BOD. Among the 3, a 48-hour storage period is the best choice for BOD results and optimal storage time. Microfiltration alone is sufficient for TDS reduction. The storage time did not have any impact on pH, and the turbidity levels were below 10 NTU across all experiments. When gray water was stored for over 2 weeks, the quality of the water went drastically down. This test was done just to see the effect of long-term storage. Even the water that did not show any significant BOD issues in 48 hours start to exhibit issues after 2 weeks. The most important information here is that the quality of any continuous accumulation of gray water will start to exhibit issues if it isn't drained often. Occasional bacteria tests in my gray water system proved that there was no bacterial presence. My research proves that shower water recycling for toilet flushing is a simple, affordable, and safe solution, particularly when the tank is emptied approximately every 48 hours. The total cost of my system is less than $500. My research also confirms that microfiltration alone is sufficient for recycling shower water for toilet flushing. Short-term storage of shower water and its use with a dual water toilet flushing system seems to be the best way to go. There is something that I want to add here regarding the collection of shower water at all times. Whenever necessary while taking a shower, I open the drain by removing the stopper to divert the shower water to the sewage. I believe that this ability to choose not to send the shower water to the tank continuously is crucial. For example, when we go shopping and come home, we do not want the initial rinsing that might have the COVID-19 virus to go inside the tank. This can be extended to several other issues when we don't want to send the shower water to the tank. I know that this is an important factor for the success of sustained quality in my shower water recycling system. If you have any questions, I'll be happy to answer them. Thank you.